Okay, welcome guys. From now on, I am starting a new series of lectures in which I would try to explain the design of reinforced concrete concepts. Starting with the introduction, it says that the design of structures is achieved by performing in general the two main steps. Okay, the first one is determining the different forces acting on the structure using proper methods of structural analysis, and this will gives you the demand on the structure, right? After calculating the demand on the structure, you can perform the proportioning all the structural members, and that will gives you the capacity. Now in any given circumstance, the capacity should be greater than the demand, so that the structure should be safe, stable, serviceable and functional. Okay, now structural concrete is commonly used in all types of buildings. Its two component materials are concrete and steel. They work together to form structural members that can resist many types of loadings. The key to its performance lies in strength that are complementary, and that is that concrete resists the compression and the steel reinforcement resists tension forces. Okay, the term structural concrete indicates all types of concrete used in structural applications. Structural concrete may be plain concrete, reinforced concrete, pre-stressed concrete or partially pre-stressed concrete. Okay, in addition, concrete is used in composite design as well. And what is composite design? Composite design is used for any structural member such as beam or column when the member contains a combination of concrete and steel shapes. For example, in figure A you can see that there is a steel shape in the middle of the column, right? So you can embed this steel shape for enhancing the strength and other properties of this reinforced concrete column. This is a typical reinforced concrete column. You can see the longitudinal steel and the transverse steel, right? The hoops and the longitudinal reinforcement as mentioned here, and you have put it a steel wide flange at the middle to enhance its properties, the load carrying capacity. Now what these three figures are presenting here is quite a different phenomena, which is called the what would you say, if you have heard about the Mendel's model, which deals with the confinement effect. And for instance, let me take you to a video that a lecture I recorded about this whole behavior and this whole phenomena, which says, let me take you to that point. It is basically about I have performed in the SAP 2000, and you can see that this is the confined concrete, right? And this is the stress strain curve of confined concrete, and when I click the show unconfined, so you can see that the unconfined concrete to the confined concrete, the properties of the unconfined concrete are much lesser than the confined concrete. This is much superior. So the confinement effect, which is actually making the concrete confined, if you apply the normal longitudinal steel and the hoops, then you can see that the confinement effect is reducing as you are moving away from the longitudinal steel, right? And at the middle it is minimum, and when you are then moving towards the next longitudinal steel, the confinement effect is increasing. So this is the confinement area of concrete with this normal combination. And when you uses, for example, the steel shapes instead of longitudinal bars at the corners, for example, this is a steel angle, right? So you have used steel angle, and you can see that the confinement part of concrete has increased. And if you replaces this hoop, the transverse hoop, with the tie plate of steel, then you can see that the confinement area increases further. So the confined concrete area increases by changing the arrangement and using the composite design, but it is used in special types of structure where strength is of much importance than other things. Okay, now what are the advantages and disadvantages of reinforced concrete? Reinforced concrete as a structural material is widely used in many types of structures. It is a competitive with steel if economically designed and executed. So the advantages of RC can be summarized as follow. It has a relatively high compressive strength than tensile strength. Okay, the compressive strength is relatively higher than tensile strength, not with comparison to other materials. It has better resistance to fire than steel. Okay, it has a long service life with low maintenance cost. In some types of structures such as dams, piers and footings, it is the most economical structural material. It can be cast to take the shape required, making it widely used in precast structural components. It yields rigid members with minimum apparent deflection. And what are the disadvantages? It has low tensile strength. It is about 1/10 of its compressive strength. It needs mixing, casting and curing, all of which affect the final strength of concrete. Okay, so it depends and it varies from person to person. The cost of the forms used to cast concrete is relatively high. It has a low compressive strength as compared to steel. Okay, the ratio is about 1:10 depending on materials, which leads to a large sections in columns of multi-story buildings. For example, the steel section would be much smaller as compared to the concrete sections. So the cracks develop in concrete due to shrinkage and application of live loads. So these were the some of the disadvantages. The codes of practice, the design engineer is usually guided by specifications called the codes of practice. Now engineering specifications are set up by various organizations and to represent the minimum requirements necessary for the public safety, although they are not necessarily for the purpose of restricting the engineers, but the public safety is of primary concern, so various organizations have set those requirements, right? Now most codes specify design loads, allowable stresses, material quality, construction types and other requirements for building construction. The most significant standard for structural concrete design in the United States is the Building Code Requirements for Structural Concrete, ACI 318 or the ACI code. So in our lectures we will use this term ACI code or ACI 318. Other codes of practice and material specifications include the IBC, which is International Building Code, the ASCE, American Society of Civil Engineers, the AASHTO, which is American Association of State Highway and Transportation Officials, the ASTM, American Society for Testing and Materials, the American Railway Engineering Association area, etc. There are many more. Okay, so you can download it from internet. I can provide it to you as well. The design philosophy and concepts. The design of a structure may be regarded as the process of selecting the proper materials and proportioning the different elements of the structure according to the state of the art engineering, science and technology. Now in order to fulfill its purpose, the structure must meet the conditions of safety, serviceability, economy and functionality as we discussed previously. This can be achieved using design approach based strain limits in concrete and steel reinforcement. Now this is the most important point, the strain limits. Okay, and we will discuss it in much detail for a better understanding. So the unified design method is based on the strength of structural members assuming a failure condition, whether due to the crushing of the concrete or the yielding of the reinforcing steel bars, right? Although there is some additional strength in the bars after yielding due to strain hardening, this additional strength is not considered in the analysis of reinforced concrete members. It will be discussed in the next slide. But in this slide I want to show you about the strain limit. Okay, for example this thing, the strain limits in concrete and steel. So as you are well aware that in a simply supported beam, when it bends downward, so at the top there will be compression and at the bottom there will be tension. So what happens, epsilon u is referring to the strain in the concrete and epsilon t is referring to the strain in steel, right? So epsilon u is the strain in concrete, which is 0.003, which is the ultimate strain at which the concrete fails, right? So in all the three cases, if you notice that the epsilon u is same 0.003, right? So what is net tensile strain? That what will be the strain in steel when concrete reaches failure? For example, here the strain in steel is 0.002, here the strain in steel is 0.004 and here the strain in steel is 0.005. So if we are using a grade 40 steel, so it's grade 60 steel, so it is just yielding at this strain, right? So this is the case when steel is yielding and the concrete is crushing at the same time, which is a balanced failure condition, and this is the most dangerous condition. This is the point where the steel is yielded and now the concrete is reaching its failure, and this is the point where the steel yields and it has got elongated much more, after which the concrete is reaching the crushing. So in the coming slides, in the coming lectures, you will see this thing, that how it affects the strain limits and the net tensile strain of the section. And this was what I was referring to while discussing this last point. If you remember that there is some additional strength in the bars after yielding, right? So after yielding, if you see that the steel is yielding right here, and after yielding it is going above. Now for the purpose of explanation, I will mention here that the red line is engineering stress and strain relationship, and the gray line, it is true stress and strain relationship, because in this curve we divide the stress by the true area. However, in this curve we divide the stress or the force by the original area. Therefore the area is same and the load is decreasing, right? So if you consider the engineering stress strain curve, so you can see that after yielding there is a much capacity of the structure, right? Because we considered that once it yields, then it will continue like a straight line, and we are ignoring all this extra additional capacity of the strain hardening and all this, right? So this portion is ignored, and which makes it more conservative. Now in this approach, the actual loads or working loads are multiplied by load factors to obtain the factor design loads. The load factors present a high percentage of the factor for safety required in the design. The ACI code emphasizes this method of design, and its provisions are presented in the body of the code. The reason for introducing this approach by the ACI code relates to the fact that different design methods were developed for reinforced and pre-stressed concrete beams and columns. Also, design procedures for pre-stressed concrete were different from reinforced concrete, and the purpose of the code approach is to simplify and unify the design requirements for reinforced and pre-stressed flexible members and compression members. And this is your reinforced concrete, the normal reinforced concrete member, right? It is a simply supported beam, point load is applied and it bends like this way, and we provide steel at the bottom because the tension is in the bottom side, right? And this is the pre-stress section. You apply a pre-stress steel here, and it causes upward bending, and when you apply the point load, it makes the beam even, and there is no effect of the load on it.